This problem's a little bit outside the scope of AP Physics 2, but if you know some calculus, it's a pretty interesting problem. So find the net electric field at point P if the rod has a linear charge density of lambda, and express your answer in terms of x naught, so the distance from point P, A, which you can see the top of the rod is at A, and then I forgot to write it, but the bottom of the rod is at negative A if you were to plot this on an axis. And lambda, as well as Coulomb's constant. So, sorry, excuse me. This is a bit of an interesting problem because, you know, you might be tempted, you know, if you say like, oh, well, E is equal to KQ over R, you may be tempted to just plug in, like, what you know into this equation. So, lambda, the linear charge density, that's just kind of like how the charge is distributed. So, over this length, it's like kind of uniformly spread out. And the way we would write that is that the linear charge density, lambda, is equal to its charge per length. So Q, the total Q, over the length. So A to negative A, that's a length of 2A. And because lambda is positive, we say like the charge on the rod is positive. You might be tempted to be like, okay, well, if that means lambda times 2a, so 2 lambda a, is going to equal q, right? Because if you multiply 2a on both sides, you could just say that, oh, E is equal to k times 2 lambda a over x naught squared. You might be tempted to say that's your answer, but this equation, like Coulomb's law for electric field, only really applies to point charges. In reality, what's going on is that there are a bunch of point charges. So, there's a bunch of these little point charges, like right here, and all over the rod, because it's uniformly distributed. So let's say there's a point charge right here, right at the top of the rod. We can call that dq, right? A very small amount of charge dq. So, dq, all right? And that's going to be a certain distance from point P. Excuse me. A certain distance from point P is going to create a very small electric field this way, right? And that I drew that arrow. So I just dropped my eraser. I drew that arrow a bit small, but it's really creating an electric field, a very small electric field, dE, right? And what we could say is, that this dE is equal to k dq over the distance squared. So our distance, let's call this height right here y. So if you think about Pythagorean theorem, x squared plus y squared equals like r squared, the distance squared. So we could say that it's equal to square root of y squared plus x naught squared. So we could plug that, we could throw that back into here, and square root x naught squared plus y squared squared, so that cancels out the root, and you get dE is equal to k dq equals x squared plus x naught squared plus y squared. And our goal, right, is that, well, every charge, depending on its height from the origin, is going to produce this sort of an electric field. If you were to take the point charge here, right, it's going to produce an electric field this way, a dE. Our goal is to sum up all of those dEs for all of the dQs, right? All the electric fields that each point charge is creating, sum it up using an integral, and then we can get our answer. Now, remember, our electric field, has two directions, right? This dE has an x component and a y component. So dEx, dEy, what you can imagine is that all the dEy's, right? All of these charges that create like a dEy, it's all going to sum up to 0 because of symmetry, right? So this top charge will have a certain dEy, like a y component downwards, but the same point charge you can find symmetrically in the negative y-axis, it's going to have an electric field upwards. All that's going to cancel out, and you can even do the calculus. It will actually sum up to 0. But and maybe I'll show that if I have some time. Right now we're going to focus on the x axis, because you can imagine, yeah, if I place a positive charge here, the net, so if I were to kind of erase sum of what I got here. But the net at point P is going to be pointing this way, right? So I'll say E, yeah, I'll just say E. So it's gonna point exactly this way. You can imagine, like, that makes sense because of the symmetry, right? There's no y component. So how do we find? So we can't just integrate like this, right? We can't integrate just the electric field because this is the magnitude of the electric field, but this is a vector. So you can't add vectors that easily. You have to add the x components of the vectors. So to get the x component of that dE, so if I were to, let's draw that again, the dE. So if this is our dE, we're trying to find the x component. So if we had an angle theta right here, we need cosine theta. So this we got to tack on. So dEx is equal to this expression times cosine theta. So with this cosine theta, we can find that x component. How do we get cosine theta, right? You could, I think there probably is a way that you can like leave the theta in there and then integrate over the angle. That sounds really painful though. Like if you tried this, you would probably be stuck in terms of when you start integrating. To make it easy so that we only are integrating with respect to one variable is we can just use this triangle created right here, right? This angle is also theta by vertical angle, like the vertical angle theorem or whatever that says these two angles are equal. So if we want the cosine of this angle, we just have to get the opposite over adjacent over hypotenuse. I pointed to the right things, didn't come out right, but adjacent over hypotenuse. So I would say that, hey, the dEx is equal to k dq over x naught squared plus y squared times x naught over the hypotenuse, and I'll do it like this, square root x naught squared plus y squared. So in this expression, we have two changing variables. We have y, right? So as you go down this rod, your y is going to change, right? Because this, if I were to, like for this dq, this is like a smaller y than this. So as you're going down the rod, we have a changing variable y. X naught is constant because we're just, right? That's just the distance from the rod. But we also have dq that's changing, right? That's in like that's the variable. Oh my god, my cough's still not gone. We have a dq, right? That's not really helping us because y is a changing variable. Like we don't, like we're integrating through the dq. Luckily, what we can say is that, hey, well, if the lambda is equal to the total q over the total length, that's like the ratio, right? Like the charge per length. That would also mean lambda is equal to dq, right? A small little charge over a small little length dy, right? On the y-axis. So what we can do is we can say that dq is equal to lambda dy. Equal to dq. So now that we have this lambda dy, we can just substitute that back into our equation. So I'm going to do it right here. dEx is equal to k lambda dy, and then times x naught, so x naught in here, over, now this is kind of nasty. We have this times the square root. This is to the power of 1. We're multiplying by the power of 1/2. That gets us 3/2 by our exponent properties. So we can say x naught squared plus y squared to the 3/2 power. Okay, now we gotta start integrating. So what we can do, I might just make some space so I can get this integral. So dEx equals this. So if we were to integrate all of the dEx's, we're going to be integrating in terms of this. What are our bounds for the integral, right? Because this is a definite integral, right? It's a set length. We're going from negative a to a. So we're integrating it from starting here, and then we're adding up all the way till we get to a. So now what we can do is we just evaluate this integral, which you could tell is not going to be fun. It doesn't look fun at all. But e to the x, what can we get out of the integral? K is a constant, lambda is a constant, x naught up here is a constant, so we can just pull all of those out. And we're left with this. dy over x naught squared plus y squared to the 3 halves. Okay, so if this was like an APFRQ, or if you're taking like this at, like if this was like your university final at, I don't know, U of I or something, they should I think give you a table of integrals. This would definitely be on it. Like this is like a really common integral in electrostatics, like especially with these types of problems. So this integral, you could do, if you're into math, you can evaluate this out. I don't know how to do that. I'm just going to use a given integral. It's going to be equal to, so e to the x is equal to k lambda x naught. It's going to equal 1 over x naught squared times y over square root x naught squared plus y squared. Alright? So we're integrating from these bounds, so we got to start plugging those variables in. So it's going to be 1 over a over that whole thing. So a, I'm just substituting it in for y, square root x naught squared plus a squared, minus the same thing, 1 over x naught squared, but this time negative a, x naught squared plus negative a squared. So what this would evaluate to, so first of all, we can kind of factor out this 1 over x squared because they're both in this term. So we could say e to the x is equal to k lambda x naught over x naught squared. Whoa, we can, cancel this out. I don't know why I said it like that. Whoa, I don't know why I said whoa, but we get k lambda over x naught. And then now we have a minus negative a over the same thing. So you're just minusing a negative, you're just adding, and these are basically the same like variables, just this is negative. So we get 2a. So you're adding them both. Over square naught x naught squared plus a squared. So that's pretty cool. And then what we would get, our final answer, is e to the x is equal to k lambda, so I'll say 2k lambda a over x naught square root x naught squared plus a squared. So now, then we can box that. Now the next question asks, what does your answer equal if a is much larger than x naught squared? Well, in that case, if a is much bigger than x naught, which really means like either x naught is really, really, really close, or a is like nearly an infinite long length or whatever, we would say that, okay, well, e to the x, it's not like a very simple limit to kind of solve for. You kind of have to be like, okay, x naught over square root x naught squared plus a squared. So I think if you were to evaluate this limit, you would probably get indeterminate form, because you would have like kind of infinity as a, and then you would have infinity here. I think that'd be indeterminate form. But and how you would solve the limit is you would say, well, e to the x. So you would kind of have to be clever. You have to kind of factor out an a squared so we can cancel out an a. So e to the x is equal to 2k lambda a over x naught times the square root. We're factoring out an a squared here, and we're going to say x naught squared over a squared plus 1. So when you factor out, when you basically when you multiply back in, you just get the top term, or the top expression. And then what we can say is, well, is that e to the x is going to equal 2k, and I'll show you guys this in a second, 2k lambda a over x naught a square root x naught squared over a squared plus 1. So now the a's can cancel, the a's drop now that I factored it out, because when you take the square root of it, just turns to a. And now we can evaluate this limit, because if x naught squared is really, really small compared to a, this term right here evaluates to 0. So we get e to the x equals 2k lambda over x naught square root 0 plus 1. So this evaluates to 0, we get 1. K square root of 1 is just 1, and we get e to the x equals 2k lambda over x naught. So you can even imagine if we just used Coulomb's law for a point charge, where we got E is equal to K2, so we'll get 2k lambda over, we got 2k lambda A over, what was it, x naught squared plus a squared. It's not, like, that was sort of close, but you could tell it was not exact, right? So when you have these linear charge densities, you really gotta be exact, I guess. It's not as simple as a point charge. So thank you for watching. My challenge for you is, can you get this? Can you arrive at the same result here using Gauss's law? Thank you for watching.